Great. So we went through the syllabus last time. We went through the math prerequisites and did that math quiz. Today we're going to start with actual material from the class for the first time. The first thing that we're going to talk about is units and converting units. I know a lot of people in here have taken chemistry and done this kind of stuff before, but it's not a prerequisite, so we're going to go through it. So just imagine something you like and just sit there quietly if you... So, units. The exciting thing is, after class today, I'll be able to give my first assignment. I'll be able to actually give you work to do. All right, well, all of the quantities that we're going to deal with in physics are measurable. You can't put anything in an equation that you can't measure somehow. And all values that are measurable, everything you measure has units attached to it. So all physics quantities have units. Like, for example, if you're trying to give the speed of something, 37 isn't enough information. You need to say whether it's 37 isn't enough to specify its speed. You need to make sure the person you're talking to knows that it's 37 miles per hour or 37 meters per second, or it has to refer to a specific set of units. Every unit that we're going to use in this class, every physics unit can be made from just 4 basic units. Those are a unit of length. So units of length are inches, feet. Meters is the one we're going to use most often. Miles. Light year is a unit of length. The second is a unit of time. So seconds, minutes, hours. The third is a unit of mass. Pounds, which is what we're most used to thinking of as mass, is really a unit of force. But people do talk about pound mass, which is the amount of mass that's required for its weight to be 1 pound of force. So I'll call it pound mass, LBM. And then the one that's going to matter for, well, grams is another one. The one that we're going to use almost all the time is kilograms. And then the last one, this is the one of the 4 that's not going to come up in this class, but that's charge, electrical charge. Those of you who are taking Physics 2, that's going to be a big topic in Physics 2, and the unit you'll use most is coulombs. But so this 4th one isn't going to matter to us. All of these, let's see, meters and seconds and kilograms and coulombs, although we're not going to talk about those, are the SI units. The standard international or SI units. And almost all our calculations are going to use those. So what I mean when I say that all units can be made from these four basic ones, well, I already showed, the unit of speed. You can use meters per second. Even though it's a unit of speed, it's made by taking the unit of length and dividing it by time. Another example is the unit of force. So the SI unit for force is called the Newton. But it turns out that 1 Newton is equal to 1 kilogram times meters divided by seconds squared. And so it's a really complicated looking expression based on those four basic units, but you can write it that way. So measured quantities are always a number and a unit, right? It's always going to be 50 meters or 66 seconds, a number and a unit. So when you're given one of these measured quantities, think of it as a number multiplied by a unit. And really that's physically what it is. If you think of a measured quantity is the length of this, right? Your units of length could be meters or feet or whatever, or you could make up a unit of length that's one of these, right? So how long is this? It's 3 times this unit, 3 of these, 1, 2, 3 makes this length. And so that multiplication thing isn't just a mathematical way of looking at it. It's really what a measured quantity is. The nice thing is, so if you think of it as a number times a unit, so for example, getting ahead of myself. So let's say 25.4 meters. You think of that as 25.4 times this unit meters. And thinking about it that way lets you, so if you treat it this way, you can treat units just like algebraic variables when you do algebra. Like for example, if you take a measured quantity of 10 meters times seconds and divide it by 5 meters, The 10 divided by 5 gives you 2. The meters in the numerator and the denominator cancel, and you end up with this quantity that's just equal to 2 seconds. And that works just the same way it would if this m and this s were just variables that didn't have specific meanings. In all scientific equations, if you do the algebra with the units, at the end, once you've gone through all the calculations, the units on the two sides of the equations always have to match. Let me give an example. You've probably at some point heard of the equation force equals mass times acceleration. That's called Newton's second law. In this class, it's going to be the most important equation we deal with. So F equals ma. Well, I mentioned just a minute ago that if we're thinking of SI units, the units for force are newtons, which are also equal to kilograms, meters per second squared. In SI units, the units of mass are kilograms. In SI units, units of acceleration are meters per second squared. And so if you think of these as algebraic variables, since these two quantities are multiplied together, the units have to be kilograms times meters per second squared, and that matches this. Okay, and that holds for every equation in this class and every equation in any science class. We're not always going to, we're going to start out this class by keeping track of the units as we go through these calculations. But it's pretty cumbersome, so we'll spend a little time doing it just so you see how you can do it. But eventually we're going to sort of stop worrying about that. But always throughout the rest of this class and any physics and whatever class you take, that always will work. Okay, so every measured quantity has units, and a lot of times you want to convert one unit to another similar type. You want to convert meters to inches or light years or something like that. So the next thing we want to talk about is unit conversions. And for these simple unit conversions, we're all used to doing it. Like for example, let's say we want to figure out how many inches are there in 3.5 feet. Okay, you could probably just think that one through. But what I want to do is give a systematic way to go through this that'll work for simple problems like this, but it'll also work when they get more complicated. So the idea is always this. We're always going to know some equivalence between the two units. So say that we're given that 12 inches is 1 foot. Since those two things are equal, if you divide something by itself, you always get no matter what the number is, 50 divided by 50 is equal to 1. Negative 6,000 divided by negative 6,000 is 1. So if you divide something by the equivalent thing, you always get 1. So we can think of 12 inches divided by 1 foot as being equal to 1. And we can also think of that as equivalent to 1 foot divided by 12 inches. And since we don't want to change the meaning of this, we just want to re-express it. So we're going to take this original quantity that we're given and multiply it by one of these two versions of 1, so it stays the same, but we have it in a different set of units. So let's take 3.5 feet and multiply it by 12 inches divided by 1 foot. Now, if you think about these feet as being like algebraic variables, you can see that those two cancel. The only units we have left are inches. And so this comes out to be 3.5 times 12 is 42 inches. Okay. So that worked just like we wanted it to. Then the question is, what about the other one? Because this equivalence always gives us two ways to express this value of 1. And we use this one, it worked great. Maybe this one will work great too, Let's try it. It's not going to work. So we'll start with, so what about the other one? The other ratio. So we'll start with our given quantity. That's the thing that we don't want to change. We just want to re-express. And we'll multiply it by 1 foot divided by 12 inches. Now nothing cancels out. And so if we go through the calculation, 3.5 divided by 12 is, so you get like 0.2917 feet squared over inches. Okay, so that is a valid quantity, and it is, that you could use those units as a measure of length. It's a real unit of length, feet squared per inches. And in feet squared per inches, this is equal to 3.5 feet. It's the same distance, but it's not what we wanted. It's not what we were asked for. So how do you know which of these two ratios to use? You always have these two options. How do you know which one to take? You always want to use the ratio that cancels out the unwanted unit. So let's go back to that original problem and see how that worked. So based on that equivalence, we have two possibilities, 12 inches over 1 foot, or 1 foot over 12 inches. And our given quantity has feet in the numerator. The number is multiplied by feet, it's not divided by feet. And so and our unwanted units are feet. We're trying to get rid of feet, so all we have left is inches. And so we want the ratio that puts feet in the denominator so that it cancels this one. Okay. So you always have a unit that you're trying to get rid of, and you need to choose the ratio that cancels that one out. So starting now, I'm going to use this shorthand approach. Instead of writing things out with the parentheses, I'm going to write it like this. So here's what we start with, 3.5 feet. And I'm going to write the whole thing as a fraction. And instead of parentheses, I'm going to just use vertical lines to say where the parentheses would be placed. So there's 3.5 feet. In the denominator here, we have 1 foot. In the numerator, we have 12 inches. Saves a few pen strokes, makes it easier to keep track of what thing is in the numerator and what's in the denominator. Anybody have any questions about any of this so far? Dave, you have a question? Oh, there's no one named Dave. I got confused for a second. That was stupid. All right. And it is Dave. No, I have not, but that would be embarrassing for all of us. All right, so the next thing, let's do this. Let's figure out how many, example, how many meters in a mile? Because like when I was in high school, I ran 1,600 meters, and my coach would call it the mile, but I'm going to really get to the bottom of this. Is it really a mile? Okay, so what are we going to use? So there are a few things that I know. Well, I happen to know that there are 3.281 feet in a meter. Yeah. And I happen to know that there are 5,280 feet in a mile. And so what we're going to do, this first example we did, this first conversion example, we did it all in one step. We knew the equivalence between feet and inches. This one we're going to have to do in 2 steps because we're actually trying to find the equivalence between a mile and meters. And so what we're going to do is our starting quantity is going to be 1 mile. We're going to use this equivalence to express that in feet. And then we're going to use this equivalence to express it in meters. So our starting value is 1 mile. So the 1 and the mile are both in the numerator. And the first multiplication I do is going to convert miles to feet. Well, I know I'm going to multiply by one of these 2 ratios, either 5280 feet over 1 mile or 1 mile over 5280 feet. In this first part of the conversion, this equivalence, What's the unwanted unit? What's the unit I'm trying to get rid of? Miles. So I want to choose the one that cancels miles. So since miles here in the numerator, I want this miles to be in the denominator to cancel it. So 1 mile is 5,280 feet. And if you did the cancellations right now, you'd see that we do get rid of miles. And if we multiply this out now, we'd have it expressed in feet. And now I want to go from feet to meters. What's the unwanted units for this step? Feet. So I want feet to be in the denominator of the thing that I multiply. So 3.281 feet is equal to 1 meter. And if I cancel the feet, I can see that the only units I have left are meters, so that's what we wanted. And now we can just multiply out the numbers. And depending on if I didn't round off too much, this comes out to be about 1,609.344 meters. Yep. Yeah, that's that calculation I just did brings that up urgently, doesn't it? I don't care about significant figures. Just round as seems appropriate, you know. I would care about it if chemistry professors didn't care so much, but I feel like they care enough for all of us. Okay, so when you run the 1,600 meters in track, you're 9.344 meters short of running a mile. So, yeah, I know, exactly. If I would have thought of it that way when I was in high school, I would have always run like 9 more meters. And then when people ask me, I'd be like, I was running the mile today. I was in a different race. Right, the next thing we have to do is the first two examples we did both dealt with one single simple unit. You know, the first one we did, we were converting. What was it? We were converting from feet to inches. So they were lengths in both cases. The second one, we were converting miles to meters. But some quantities have these units that are made up of more than one simple unit. So let's say that we want to convert 61 miles per hour to meters per second. This is the way it's going to come up in this class most often is you'll just be given a value in terms of things that are not SI units, and you'll want to put them into SI units most of the time to do the calculation. Okay, so our starting value is 61 miles per hour, and I'm going to write that as, let me give some equivalencies first. When you do problems like this on tests, I'm always going to give you the equivalencies. You don't have to remember, you know, how many feet are in a meter or anything like that. So let's say that our conversions, well, let's use the one we just came up with. 1 mile is equal to 1,609.344 meters. Yes, that's just because I rounded off too much. That's a significant figures issue, but we don't care about that here. How much, like how loose would I have to be with significant figures for you to go from being like happy about it to starting to be like concerned? We'll find out. And also we know that 1 hour is equal to 60 minutes. And then 1 minute is equal to 60 seconds. And so now we have all the equivalencies we need. I'm going to take our starting quantity. So that's 61. Like I said, we're always going to have, for the whole thing, a numerator and a denominator. Where does the miles go, the numerator or the denominator? Yep. So we have 61 miles. And where does the hours go? Yep. So we'll start just like this. And the first thing I'm going to do is convert the miles to meters. So in that calculation, what are the unwanted units? Miles. So I want to cancel the miles that are in the numerator here with miles in the denominator here. And if you do the cancellations, you see that, okay, now if we multiplied this out, we'd have units of speed that were meters per hour. But I'm just going to keep multiplying on the same fraction now to go from hours to minutes. If I'm trying to go from hours to minutes, what are the unwanted units? Hours. And the hours are in the denominator here, so we need hours in the numerator to cancel them. So here we have 1 hour with 60 minutes in the denominator. And this hour cancels this hour. And so now if we multiplied out the number, we'd have units of meters per minute. So the last step is we want to go from minutes to seconds. What's the unwanted unit? Minutes. So I want to go 1 minute over 60 seconds. Cancels the minutes. And the units we have left are meters over seconds. And it comes out to be something like 27.26 meters per second. And now, by the way, now that we have this equivalence, in the future you could use that 61 miles per hour is equal to 27.26 meters per second. Like, for example, let's say now we want to know what 20 miles per hour is in meters per second. So start here. And we know that 61 miles per hour, that's in the denominator, is equal to 27.26 meters per second. That's in the numerator. do all the cancellations. The miles cancel, the hours cancel, and can someone have a calculator? I don't have that. $8.937. 8.937 meters per second. The last kind of conversion that we have to do is sometimes these basic units are raised to an exponent, so we have to know how to deal with that. So let's say we want to convert 32.2 feet per second squared into yards per minute squared. So our starting value is 32.2 feet over seconds squared, and I'm going to write that instead as seconds times seconds in the denominator. The equivalences, let's use, so 1 yard is equal to 3 feet, and 60 seconds is equal to 1 minute. Okay, so for the calculation, we have 32.2 feet over seconds times seconds. Let's first convert from feet to yards. So we need the feet in the denominator, yards in the numerator. And if you cancel, now our length units are yards. And now we want to convert seconds to minutes. The unwanted units are seconds. So we want to multiply by 60 seconds over 1 minute. Here's the key thing. Doing this one multiplication of 60 seconds over 1 minute only cancels one of these seconds. These are canceled. Okay, so if all we did was this, what we would really have is multiply out the numbers, and it would give us this acceleration in yards per seconds per minute. Okay, and that's not what we want. So we have to do that multiplication one more time to convert the other seconds to minutes. So we'll multiply again by 60 seconds over 1 minute. That cancels the other second. And now the units that are left are yards per minute squared. If there's anybody who does a lot of unit conversions and you're happy with a different way that you do it, feel free to use whatever method you want. Just this is a way that works. So if you're looking for a new method, why not this? Okay, that comes out to be something like 38,640 yards per minute squared. Any questions about that? Okay, let me give you one to work on, and please talk to each other, share notes, When you finish, look at each other's answers. So let's say, you know how big a meter is, like a little bigger than a yard. So like this big, this big, this big, you know. So imagine this big 1 meter cube, okay, sitting on the table. So here's this big block where all the lengths are 1 meter. And the height is 1 meter. And the depth is 1 meter. And now imagine that this, or imagine it being an empty box, okay? And now imagine little tiny cubes where all the lengths are 1 centimeter, okay? The question is how many 1 centimeter length, you know, where every side length is 1 centimeter. How many of these 1 centimeter length cubes will fit in this big box? The way this is a conversion question is you're starting with the value 1 meter. You're starting with that big box, and you're trying to re-express it in centimeters cubed. So this is the same thing as converting from 1 cubic meter to centimeters cubed. Okay, so take a minute and see if you can work through that, compare answers with each other, make a new friend. And feel free to, you know, talk out loud. You don't have to whisper. Okay, so our starting quantity is 1 meter cubed. I'm going to write that as 1 meter times meter times meter. Yes. Well, the 1 cent, I should have said this. Maybe you remember this. 1 meter is 100 centimeters. So we're going to multiply by, we're going to use the equivalence that 100 centimeters is 1 meter. So I'm going to start with 1 meter times meter times meter. I'm going to multiply by 100 centimeters over 1 meter. And that cancels one of our unwanted meters. And so I'm going to have to do it 2 more times to cancel all of these. 100 centimeters over 1 meter. And then the third one, 100 centimeters over 1 meter. And if you cancel them out, you can see that now we're finally left with only centimeters. And so the number that we have is 100 times 100 times 100, which is 1,000,000 centimeters cubed. So 1,000,000 of those cubic centimeters to fit into a cubic meter. Any questions about that? Okay, the next thing we have to talk about is scientific notation. And the idea of scientific notation is that any number can be expressed as one non-zero digit then a decimal point, then a decimal, and then times 10 to an integer. And so any number, when you put it into that form, it's in scientific notation. I'll give two examples. The first one, if you have the number negative 3,461.45, that's the same thing as negative 3.46145 times 10 to the third power. And the way that works is 10 to the third power is 1,000. So you're just multiplying this 3.46 blah, blah, blah times 1,000. And it gives you, 3,461. Changing things into scientific notation and back never affects the sign. So if it's negative, it's negative. And you can see how this is a nice way to write numbers that would be really big. Imagine if we had a number in standard notation that had 50 zeros before you got to the decimal place. And you're trying to read that in standard notation, you're going to have to count all these places. And if you're off by one, it means your answer is going to be off by 1,000%, But in scientific notation, it's really easy to express that. It would be some number times 10 to the 50. It's also a nice way, a way to avoid errors in writing numbers that are really small. Like, for example, say that your number is let's say there's 4 zeros, 0, 0, 0, 0, 815. The exponent? Yes, that's right. And I'll give a method for that. Okay, so this is equal 1, 2, 3, 4, 5. This is equal to 8.15 times 10 to the minus 5. And again, you can imagine how tedious it would be to have to count these zeros if they went halfway across the page. And again, if you're off by one, you're off by 1,000% in your answer, which is a pretty big error. If you're shooting for an error less than 1,000%, you need to set the bar higher. One thing that's nice about scientific notation is you remember, for those of you who've talked about significant figures before, when you're you have a number in front of you and you have to determine how many significant figures it has. There are all these rules for how to treat zeros. Do you remember that? Like if the zeros are to the left of the decimal point, they only count if there's another non-zero number before the decimal point, or if there's a decimal. There's all these rules, right? if you're writing numbers in scientific notation, you don't have to remember any of those rules. So it's really easy to determine the number of significant figures for a number written in scientific notation. In scientific notation, just every digit before the times 10 to whatever is significant. Okay, so for example, let's say 800,100.009 how many significant figures does this have? Well, if you're thinking about it in terms of the rules, it's kind of a pain, you know. But if you express this in scientific notation, in this case they are, yeah. If you write this in scientific notation and you see that in order to write it in scientific notation, you have to write 8.001000009 times 10 to the 1, 2, 3, 4, 5. In order to give the same number, you have to write it like this. And now you know that all of those are significant. So 1, 2, 3, 4, 5, 6, 7, 8, 9 significant figures. Whereas this 8000000, yeah, I mean, I suppose you could write this in scientific notation as 8, no decimal point, times 10 to the 5. And this clearly has just one significant figure. So what I'm going to do is we need methods to go from standard notation to scientific notation, and from scientific notation to standard. I want to say one thing before I do that. A lot of times in this class, I'm going to write. So let's say I'll sometimes write. Say we have this number 5.65 times 10 to the 4. I'll sometimes write that as 5.65 capital E4. Because that's how you enter it into your calculator. And it saves a couple pen strokes for the extremely lazy. But just, you can do that in this class. I don't mind. Maybe, I think there are probably classes you'll have later where they don't like that so much. But just be sure that you don't do this. This is not the same thing as 5.65 e to the power of 4. Okay. This has a very clear meaning, and its clear meaning is not the same as this, This is saying 5.65 times e, which is like 2.71 something, to the 4th power. That's different than 5.65 times 10 to the 4th power. Okay. So don't do this, but if you want to do this, that's fine. Anybody have any questions about that? I was at a meeting like my first year here or something, and one of the chemistry teachers complained that one of her students who was in physics was like writing stuff like this in her class, and it made her so mad. And I knew that it was my fault, but I didn't say anything. Okay. So now the two methods that we need to be able to go from standard to scientific and scientific to standard. If you're used to doing this and you're happy with the way that you think about it, feel free to keep doing it your way. This is just for anybody who has trouble with this or hasn't done it before. These methods I'll give you will always work. So the first one is start with a standard number and put it in scientific notation. So this is to put a standard number in scientific notation. And as I describe these steps, I'm going to do them on this number, negative 541.6. Okay, so the first step is count the number of places, and we're going to count the number of places. We're going to call it capital N. Count the number of places that you have to move the decimal point left or right so that the number has one non-zero leading digit. Leading digit is, before the decimal point. Okay, so with negative 541.6, how many places do we have to move the decimal point? And do we have to do it to the left or the right? 2 places, so n is equal to 2. And did we move it to the left or the right? Yep. Left. And now the second step, if we had to move it to the left, then we're going to multiply by times 10 to the positive n. If we had to move it to the right, we're going to multiply by 10 to the negative n. So in our example, we had to move it 2 places to the left. So our number is going to be negative 5.416 times 10 to the positive. Any questions about that? And then the second method we need is to go to put a number in scientific notation into standard notation. For this one, I will, my example number will be 6.52 times 10 to the minus 4. So the first step is read the absolute value of the exponent and is it positive or negative? Okay, so the absolute value of the exponent, let's call that absolute value n. Okay, so what's n in this case? What's the absolute value of that exponent? 4, and it's negative. And now if it's positive, move the decimal point n places to the right. And if it's negative, move the decimal point n places to the left. Okay, so for this example, it's negative, and n is equal to 4. So we're going to move the decimal point 4 places to the left. So I'm going to start with my 6, 5, 2. And I'm going to go from here, 1, 2, 3, 4. Fill all those empty places with zeros. And that's the number in standard notation. Any questions about that? So the last thing that I want to talk about today is prefixes like milli, centi, mega, micro. Here are the ones that are going to be most important to us. Micro, its symbol is the Greek letter mu, and you can think of it as meaning times 10 to the minus 6. The next one is milli. That's the symbol for that is a lowercase m, and that means times 10 to the minus third. The next one is centi. That's shown with a lowercase c, and that's times 10 to the minus 2. And then kilo. That's shown with a lowercase k. That means times 10 to the third, positive third. And then the last one here is mega. That's shown with a capital M. And that means times 10 to the 6. Yes. So for example, bless you. Um, mhm. Yeah, I'll go through a couple examples. I'll do one with micro first. So let's say we want to express 246, well, okay, let's say microseconds in seconds. Well, what we're going to do is just replace this micro symbol, that prefix micro, with times 10 to the minus 6. Like those two just mean the same thing. And so 246 microseconds is 246 times 10 to the minus 6 seconds. And if we wanted to put that in scientific notation, we're going to put this in scientific notation. We're sort of in this pseudo-scientific notation right now, but we need only one leading digit. So to do that, we're going to divide this first part by 100 to make that 2.46. And if we divide this first part by 100, but we want to keep the whole thing the same, meaning the same number, that means we have to multiply this by 100. So the second half by 100. So that gives 2.46 times 10 to the minus 4 seconds. Here's another one. So let's say that we want to go from this is going the other direction now. Let's say that we want to figure out, we want to express 540 grams in kilograms. Well, we know that 1 kilogram is equal to 1 times 10 to the positive third grams, because this kilo means times 10 to the third. And now we can just do it as a normal unit conversion. So we'll start with 540 grams. We want to cancel the grams to get to kilograms. So in the denominator, we'll have 1 times 10 to the third grams. In the numerator, we'll have 1 kilogram. The grams cancel, and we end up with 0.54 kilograms. Any questions about that? In the lab next week, you'll get some practice doing this sort of thing. I think, so now we've covered enough stuff that you can do the problems that are assigned for today. I don't think there's any of those prefix problems in there, but we'll do those in lab next week. Okay. Anybody have any questions about any of this? Okay, have a good weekend.